I can do just the intro and relate to the previous talk. So I'm Henri, I'm the co-founder at a company called OKcontract, where we have a public good mission. We strive to release everything we do as permissively open source, so MIT or Apache. And we got funding, in fact, from Protocol Labs initially that got us started. And then we also got large grants from Optimism and StarkNet and other projects. And here I'm going to show you the result of this and how it can contribute to the ecosystem. And maybe we should wait until there's some come back, or
I think this is pretty much it.
This is pretty much it. Okay, let's go. Let's go. Okay, let's go. So. Okay, what's functional reactive programming? And who's familiar here with RxJS, for instance? Yeah.
Oh, with what?
RxJS or ReactiveX. Yeah, perfect. Okay, so there's a framework which is called Functional and Reactive Programming, FRP, which simplifies basically how we handle complex dynamic data flows. And this is especially useful when we have lots of asynchronous data, real-time data feeds, etc. And this applies to OneLib, which you know here, which is libp2p, of course. It's massively asynchronous. Every example is full of awaits. So FRP is based on observables, and they compose these asynchronous event-based programs by using observable sequences. So some say it's Lodash for events. And this is a very short example from RxJS, where you derive your events. And for instance, we're increasing a local definition of count. And then we subscribe to it, for instance, to do something. And when you use this framework for FRP, there's a lot of primitives that you put together. And often it becomes complicated, and this is the main drawback, is that most of the JavaScript developers think it's too complicated. So it's great, but they have a hard time managing it and building complex application with it. And this is exactly the problem we are trying to solve here. So it's a simplified, we call it functional and reactive, because it's functional programming, because it's reactive, but it's not FRP. We don't follow the same observable framework. And we took inspiration from spreadsheets somehow, and I'll dig into this quite a bit. So because of that, there's much less primitives and a bit more work in the library implementation itself on automation. And somehow it's the risk of FRP. So let me know if you think that's a good definition. That's the first time I'm using it. So yeah, well, how it works. So basically, we have two types of cells, which are cells a bit like a spreadsheet: value cells and map cells. So basically, those two types of cells are value cells, which you can update from many things, including the user interface, for instance, which you can set. And that can be derived into mapped cells, which basically apply a function. Like, for instance, we can compute the sum. That's very easy, of course. AB then gives A plus B. And which recomputes this, everything, the cells changes. So how do we use it? The basic usage is we just import sheet, like we create a new spreadsheet somehow. It's const sheet equals new sheet. Then we can create a cell. And for instance, we can create a cell which contains the constant one, super easy, sheet.new one. And here are some more things. So we abstract away all the asynchronous computations. So for instance, you can also create a cell which is a long computation, which is a promise. But basically, we don't need to wait for it. We just define the promise as the definition of the computation, and we can map those cells together, and including, for instance, mapping let's say, the sum of A and B. And even if we know that this one is a promise, but we don't need to take care of that. When we compile basically the whole definition, it makes a graph, and the runtime of it will wait when it's necessary and recompute everything. And the computation themselves as well can be asynchronous. Like we can map some inputs into another long computation, which is as well a promise, and we abstract all this away. So how then do we access the values? There are basically 3 ways to access the values. The first one, so all the definitions are synchronous. So basically, we just define the graph of our computations, and the value access is, in retrospect, is asynchronous. So we wait when we want a single cell value, we can wait for it, knowing that the whole graph is being recomputed. The immediate value is accessible, though, at dot value, but that might be invalidated because you don't have then properties that it's a consolidated value. You don't know that, but on the rare case, so just a warning, we might rename this because it's dangerous, so maybe we'll call this unsafe value of something in the next iteration. And lastly, we have subscriptions, which are like for EricJS, a reactive subscription to a given value, but they don't update the graph themselves. So, yeah, we're talking a lot about the graph, and this is a representation that is basically auto-generated by what we call the debugger. I'll get back to this in a moment. And this is, for instance, when we define a program, we generate the whole compute graph. Like we have here an array which is made of several items, and basically we map functions to filter that array. This is the filter map here. We can update the function. We have 2 functions, so I'll get back to this. And we map this, and then we compute the sum of the filtered value of that array. And basically, that is, so I should have shown the code for this. But basically, it generates this. But we'll see, we have some feature here, like dotted dashed lines. So we'll get into this. But just the idea is we define a program. The program builds statically a graph, and then the graph, of course, reacts. So let's talk about graph updates and memory management. So basically, at any given time, the graph defines this functional reactive program. But to ease, let's say, building more complex application, including GUIs, we need sometimes imperative updates to the graph. So at each time, the graph is valid, but we can add new definitions, of course, to the graph, or because transformation of existing cells, unless setting the value of an existing cell, is not allowed because this enables us to do a lot of statistical analysis and doing much more in the safety part of the runtime. And I should have had a slide on these benefits, but there's not. And that includes memory management. So we can manually delete a cell when it's no longer needed because, for instance, that part of the computation is the user moved away and we don't need that. And as well, we have one feature, which I'll show, of proxies. We can automate and make it very easy for the developer to delete the cells. And finally, we have a third feature here, which is garbage collection, and which is usually meant to be used by primitives that map into arrays. So, what are proxies? Proxies are a way to create subgraphs, basically, and to attach or detach subgraphs. So basically, we can easily create a new proxy from the sheet. We can create new cells in a proxy as if it was the global cell, the global sheet. Sorry. We can map normally, and when we're done with a proxy, we can destroy that proxy, and that the subgraph is gone from the main graph and won't take resources recomputing things when we don't need them. Okay, so back to the compute graph. We can define these proxies, etc. And again, yeah, we notice those dashed lines. Those are pointers. So pointers are a very useful feature when we want to define basically several possible changes statically to that graph structure. And basically that arrives a lot, for instance, when we have a condition that gives a given cell. And depending on this, then we'll remap basically a subgraph as well, but dynamically in the runtime to that given cell below. This pointer cell will be mapped to something else. And since the pointers are common abstraction, a base abstraction, you can, I would say, breathe normally. Like you can get normally the value of a pointer cell, you can map it, etc., etc. And this is very useful when building bigger applications. And talking about building bigger applications, one added benefits of this type of programming is basically the debugging. So we can create a debugger for a global sheet, and in the next version for proxies as well. And for instance, you can generate a graph, viz.graph, like you saw of that graph. And as well, if you are building something front-end in the browser, you can define, for instance, you can inject the debugger, which has a lot of commands like to follow the path of dependencies at a given time, to print the value of a cell, etc., into the window, so to the main console of your browser. And one thing which is very key is for print, of course, to print the value of a cell and print the dependencies both ways. And basically, it's very useful to inject P, so you just type P and a cell number. Because what I didn't tell right now is that all cells have a unique ID, which are numbers and fresh numbers, so they just keep increasing. One particular feature is that it's compatible with Svelte stores. So if some of you have used Svelte, the Svelte store interface is pretty simple. And so we support basically the cell syntax to subscribe to a given cell value, and as well as the shorthand $cell equals any kind of value to update a value cell only. And we are in the process of releasing several libraries to work with Svelte, including a toolkit for components that you can reuse, enabling very easily to have your whole computation in, let's say, a pure TypeScript libraries, and as a cells, and basically expose those cells to your user interface, to components, without a lot of coding, because you just pass the cells directly, so it's very efficient, and it benefits from the graph updates. Another thing is when we are building more and more library with cells, and this is where I'm going to libp2p.js in a moment, basically it enables to have a good composability in the built artifacts, the large JavaScript code base, between different libraries. If all the libraries are built with cells, you can easily blend the subgraphs that comes from different computation and put them together and benefit from something which is extremely cool, is you have the global graph, and when you make updates, the runtime optimizes the recomputation of the cells. And this is, in fact, we were, at first, when we implemented, we said, oh, we didn't put optimization. It's going to be way slower than if you write a dApp manually. Wrong. We found out that it's way faster, like the interface reacts much faster than what we had implemented purely manually early on without cells. Why? Because of those updates. Because when everything's asynchronous, you, as a developer, usually package functions in different packages, different libraries, etc. And you wait for things, and it's not optimal. You don't know, as a developer, if you compile your whole build, what will be the optimal way to react to any value change across libraries, across components. But if you're using a global graph, then, of course, we optimize the runtime and minimally recompute everything when a value change. So the bigger the graph, the merrier. OK, let's time for a small demo. So I hope, yeah, it's working. So basically, this is just a to-do MVC. But because we can display the graph, so we can print the graph directly. So for instance, we know we have a list of to-do. We compute the length to display the 0 item here. We also sort, so we have a sorting to put the done task at the bottom. And here we already have defined the sorting computations, even if the list is empty. And we also have a mechanism which we see here is detached to select, have a given selected item from the list, because we want to compute the hash as an asynchronous function. And now it's pointing to a null cell because we didn't select anything. So if I just add foo to here, oh, okay, so in my app I have foo, which appeared in my to-do MVC example. And then we see, oh, we have the item foo, which popped up. It goes to being sorted, to have the sorted list. The length is being, the graph doesn't change here, but we still have one item, and we didn't select anything. So the null selected and hash computation is null. The red color here when we generate the graph means that all these values are null. So, and these are objects, and this is a number, and it helps a bit. So for instance, here I can add another one, and now you see we have two items, and which are sorted basically on our result here. If I select one, then okay, the UI, the CSS changed, but basically now you can't see it clearly, but it's lightly blue because it's selected. And now since it's selected, you see that, okay, now it's not detached. Null is being detached because the null cell is still here, but nothing points to here. And basically, the one which is selected is bar. Now I selected bar, slight blue. And it's selected, and we compute the hash. The hash is displayed here. And this was an asynchronous call. But still, if we look at the code base, there's no async. I can show you this in a moment. So, and basically, this is how you can have some graphs. So maybe we don't have time for to see the actual implementation, but you could go, I'll publish this repo demo very soon. It's not. But that was just to give you a small example here. So, in real life, the graph can be, of course, much bigger, and this is also zoomed in. But I can tell you this is extremely easy because we see the whole state of the whole computation of a DApp, and we see exactly how it reacts, where it points to, and if there is a problem, if something stuck, you see like a large red area, and you see, oh, what is we also have in the debugger a few functions to see the first undefined function in a path or first null in a path. And basically, we see very easily where the problem is. So it's also a very good way to debug. So, yeah, I have 5 minutes left. Yeah. Yeah. Okay. So, okay. Let's see, for instance, how it can be used with libp2p.js. And the first thing is to migrate an example, so which is what I did on my way here. And I tried the js-libp2p example chat. And I'm not sure it's done perfectly, but we will see. And it enables integrating, so we'll see. Let me go here. So it's another window. And yeah, so basically here, maybe I should and make it a bit bigger. You tell me if you don't see. So basically, you know, who's familiar with the original example of that? Okay. So basically, what it changes? So now I'm seeing that we didn't export the definition for JS and only TypeScript. But we'll add them. So basically, we just create here the sheet, the debugger as well. And I'll show you the graph in a moment. And the proxy, because it's a good practice to do a proxy anyway, even if you only have one. And then, so how it works. So if you're familiar with the original, let me show you here. And can I zoom here? I don't know. Okay. The original version, basically, of it, you know, was having some await promise.all created JSON, and then await, and we were waiting for a lot of things, and it's valid only one time, because here, if let's say if the config changes, then we would have needed manually to say, oh, the config has changed, so we need to rerun the run function. But not so with cells. So let me go up to the right one. Okay, we just say, okay, now we have our proxy. So basically, the ID dialer is just proxy.new of the create JSON. The id listener is just proxy.new, the create from JSON. This is async, but we don't need to care. It will be computed when it's ready. And the node dialer as well. So we map from the ID dialer, and we call create the libp2p with the dialer as a function here. Same for the listeners. The listeners was only used as a console log. But it's a good practice anyway if we want to have the list as a listener, as a value. It's available as a value. So basically, we just map from the dialer to get multi-address, and we map it to the list of address to string. So this will return the array. So here, sorry, we don't have the types because it's a JS and not DS, but we can export for JS next time. And then we use a subscribe because it's just a console log. So we just subscribe to the listener to display the console log of this. Same goes, so we dial to the remote peer by mapping the ID listener. And then, finally, we get to the stream, which is mapped not from a single cell, but from 2 cells this time. So basically, we call then proxy map, because it's not, when we call ID listener.map, it's just 1 cell, and we map directly to the value of 1 cell. But if there are several, then we need to do it at a proxy level or at the sheet level. And basically, we map these 2 cells with the function node dialer and listener multi-address, where we basically call the dial port protocol to create the stream. And finally, we subscribe to the stream. An added bonus here for debug, we call the debugger to generate the graph of this demo. So how it works. I didn't convert the listeners. No, I converted the dialer. I mean, and the listener. Did I try? No, this one. Sorry, this one is the old version, but it was a bit different. So how it works? Is it working? So basically, we start the listener. We start the dialer. We can see. Okay, I can compile if I want to. And see the structure, very simple, of that example. So basically, we have the ID dialer, which goes to the node dialer, and to the stream. The listener multi-address is here, the ID listener is here, and finally, from this, we compute the list of listeners. And those are the cells in that single demo. So now the listener is ready. We start the dialer. So it's run twice, so I don't know the internals of the libp2p.js enough for that. So we'll have to see why there's a state transition. Maybe we can optimize a few things. But then, okay, if we say hello, and we get back here, okay, hello comes. So let me come back where we were. Okay, so basically, here we just migrated an example. And this is useful because so it can benefit from global debugging if you have an app which is using cells elsewhere, like we do at OKcontract, where we are writing everything we do using cells. And will benefit as well from new features. But I would say what would be even cooler would be to use cells to implement internals of libp2p.js directly. Because then we would have finer granularity and better reactions of everything. And basically, the whole libp2p.js will be its own subgraph that we can attach to anything and have maybe optimal sub-reactions to things. Who knows? Probably it optimizes the runtime of it in a real app. Maybe right now, libp2p.js recomputes too many things. Who knows? Okay, so that was it, and of course, no, I should have added the last slide. It's missing in the talk. It's github.com OKcontract cells, and this is of course MIT license. Okay, so that's cells.